We already mentioned multilevel regression and post-stratification, or MRP, or even Mr. P on this podcast, but we didn't dedicate a full episode to explaining how it works, why it's useful to deal with non-representative data, and what its limits are. Well, let's do that now, shall we? To that end, I had the delight to talk with Lauren Kennedy. Lauren is a lecturer in business analytics at Monash University in Melbourne, Australia, where she develops new statistical methods to analyze social science data. Working mainly with R and STAN, Lauren studies non-representative data, multilevel modeling, post-stratification, causal inference, and more generally, how to make inferences from the social sciences. Needless to say that I asked her everything I could about MRP, including how to choose priors, why her recent paper about structured priors can improve MRP, and when MRP is not useful. We also talked about missing data imputation and how all these methods relate to causal inference in the social sciences. If you want a bit of background, Lauren did her undergraduate in psychological sciences and math and computer sciences at Adelaide University with Daniel Navarro and Andrew Porforce, and then did her PhD with the same advisors. She spent 3 years in New York with Andrew Gellman's lab at Columbia University, and then moved back to Melbourne in 2020. Most importantly, Lauren is an adept of crochet. She's already on her third blanket. This is Learning Bayesian Statistics, episode 34, recorded November 4, 2020. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.com. That's learnbayesstats.com. Do you want to support the podcast and unlock exclusive Bayesian swag at the same time? Then you can visit my Patreon page at patreon.com/learnbayesstats. Starting at €3, you can get various benefits like the private MBS Slack channel, early access to special episodes, selecting questions for episodes, or even coming on the show. You'll get more details at patreon.com/learnbayesstats. Thanks a lot, folks. I'm very grateful for any support you can bring me.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman? Is it because of my looks or the fact that I talk like I'm mad for books? Either way.
Hey folks, I have good news for the podcast to bring you. Learning Bayesian Statistics just got its first sponsor. In addition to the Patreon, this is a way to support the show, improve it, and bring you ever better content. I only want to work with companies I know and like, though, so I'm a bit picky, but I'm very happy to announce that the very first sponsor of the Learning Bayesian Statistics podcast is no other than Tidelift. I'll tell you more during the show, but basically Tidelift is making open source work better for everyone, users, companies, and core developers, which of course I find very fitting for the show. This whole podcast wouldn't exist without the wonderful people who give their time and talent to build the open source packages we all use and love. So thank you, Tidelift, for supporting the show, and make sure to listen to their dedicated segment during the show to discover how they help open source software. By the way, if you are a company and want to support this podcast, or if you know companies that would be interested, please get in touch with me and we'll see what we can do together. Okay, now let's talk about survey data and all their challenges with Lauren Kennedy. Lauren Kennedy, welcome to Learning Bayesian Statistics.
Thank you. Great to be here.
You bet. I'm super delighted to have you on. First, because you work on topics I find fascinating and that are close to my heart and topics of interest. So I have skin in the game for this episode. And also for listeners, we are recording this on November 4th. And for me, it's the morning in Paris. For you in Australia, what time is it? It's 7 p.m., something like that?
20 past 8.
20 past 8. Okay. Oh man, that's 10 hours
yes.
before me. So we are in the middle of very nail-biting US election where, again, there was a polling error. For now, it seems to be about 3 points on average. So it's like classical polling error. It's about the same magnitude as in 2016. But again, it was in favor of Trump. I would argue that that's why you have forecasting models that estimate uncertainty. And that's why with Andrew Gelman and Merlin Heidemans, we highlighted the fact that a 7 or 10% chance of Trump winning is not at all negligible, although it's not very probable, but it can happen. So we don't have the results for now, but it's like super interesting to have that in the background, because with you today, we're going to talk about, among other, survey data, the challenges of survey data and how to solve that, or at least be able to use that for statistical analysis and hopefully causal inference. But first, my first question is really crucial. Why are you called Jazzystats on Twitter or on your website?
I mean, isn't it a great name?
Yeah, that is, but I want to understand where it comes from.
Well, I feel like, you've got to be a bit enthusiastic about statistics, right? I was in psychology. You have to be very enthusiastic when you teach so that the students know how great it is, because statistics get a bit of a bad rap. But no, it actually, my husband came up with the name. This is terribly embarrassing. I shouldn't say this on a podcast, but whatever. My cat is called Jazz, and so we say Jazzy Cat a lot because she's a very good cat. And so then I was thinking about what I should make my website, and Lauren Kennedy is a very common name. So all the names were taken. So Jazzystats, that's good. It's cheerful. I like being cheerful. I think that's good.
Yeah, this is great. Congrats on this. And I hope Jazzy Cat is doing okay, by the way, with all the lockdown and so on.
She is. She's very spoiled at this point because we've been home for 3.5 months with her.
Perfect. That's how a cat should live. Let's start by your background, actually, because you started doing psychological sciences, but you also did math and computer sciences from the beginning. So how come? What's your story, basically?
Right. It's not a very normal story, really. So actually, in high school, I loved maths and science. And very much I liked both of them equally, and I didn't really know which one I wanted to focus on. So I ended up applying for and getting into an engineering degree, which I thought was the combination of the two, but turned out to be not quite the case. So I changed degrees after my first year into psychology, which was great fun. But I had all of these prerequisites that I'd filled in maths and computer science, and I was sort of enjoying the maths courses. I've always enjoyed maths, so I just started doing electives to fill up my course load. And eventually I did so many electives that I got a second degree with a major in statistics. So that's really how it came about, through love of statistics and of math. And I guess it was good. And actually I was really lucky in psychology because I had amazing mentors, Danielle Navarro and Amy and Andy Befores. Mm-hmm. I think they picked me out in second year or third year, and they had me sort of hanging out in their lab and working with them, which was great fun. And I went on and I did my honours with them and then my PhD with them. And so the whole lab was very Bayesian, not in terms of Bayesian data analysis so much, but in terms of Bayesian models of the mind and how we learn. So it was a very strong Bayesian group. And so when I started doing my PhD, I sort of started getting into this idea of how do we actually analyze the data that we have in psychology? And so I think initially I was supposed to do cognitive models like the rest of the group, but I was just super interested in data analysis. So I spent a lot of time thinking about heterogeneity and measurement and statistics and all of these things that go on when you have people helping you out and giving you data and you're trying to learn something from it.
Yeah.
I don't know, is that too much of an introduction? I guess
That's perfect. I love it. Yeah, that's great. So that means that, at the beginning, you were interested in how the brain works, how we make decisions, and so on. And with time, you focused more and more on the methods of how we can learn about the brain and how we make decisions and so on. And so that makes sense to me that during this path, you encountered Bayesian methods, because we often say that the brain works in more Bayesian ways. So that's totally logical to me. And that's really cool to see that, that you can start with an applied social science. And then if you want, focus on more methodological and math-heavy stuff because you do more of that now. So before diving into your stats work, can you tell us now what part of the social sciences you're focusing on right now, and just define it for us?
So that's actually, it's a really tough question. So specifically, I'm really interested in the parts of social science where people are providing data and we're trying to analyze it and learn from it, right? So these are experiments and they're surveys and they're sort of people filling out scales for us. So I'm really interested in the data that comes from people because it has really unique properties.
Yeah.
I don't know if it has a definition. In psychology, we kind of call it psychometrics, which sort of incorporates measurement and analysis and sort of understanding of scales. I don't know if it has like an actual name, but it means you get to hang out with a lot of cool people who are working hard at trying to analyze this data, and there's lots of really cool problems in it too. So I'd super recommend it.
Yeah, that means actually you can work with a lot of applied researcher, and you come into the project and help people understand how they can use the challenging data they have on their end. Right.
Yeah, so it's interesting, right? So I work a lot with survey statistics. I work with survey folks who are running the surveys and also statisticians who are interested in analyzing it. But at the same time, I have my whole cognitive science background, right? And so I still talk to a lot of these people who run very sort of basic sciencey experiments and think about how we learn information. And I think the connections between the two are just super strong and super interesting.
Yeah, definitely. We're going to dive into that a bit later. And actually, I'm curious, because you do a lot of Bayesian statistics, and how does that work with the people you're working with? Like, how Bayesian are the fields you're working with, and how does that interact,
Yeah, so psychology is interesting because it sort of had a Bayesian sort of push as I was doing my PhD, so it was kind of timely for me.
Yeah.
So I feel like there's kind of like quite a lot of Bayesians and there's a lot of Bayesian thought out there, and there's quite a push towards it. Sort of within the survey world, there are a lot of Bayesians out there, especially like the folks who do MRP like me, but there are also a lot of folks who would use more traditional methods like regressions and just sort of more weighted frequentist methods. And, that's fine too, but you have to be aware of like the benefits of these things and the negatives as well.
That's always something I'm wondering about, like also like just for, the diversity of your co-authors pool. I'm wondering about that, like how diverse is your co-author pool?
How diverse is it? I'm still young academic-wise, so it's getting more diverse with time, I think. I super love talking to people. I think that's kind of the nice thing, like just getting to talk to people and hear what they're passionate about.
Okay, but so that means that it's not necessarily a blocker, like to be focused on Bayesian statistics, at least in the field you're working in.
No, not at all. Not at all. Lots of open questions, lots of interested people.
That's great. I'm sure the listeners will be thrilled to hear that. Actually, do you remember how you first got introduced to Bayesian methods, and why did you find them attractive?
Okay, so this is a fun story because I actually didn't find it that attractive. So I did sort of a very traditional frequentist undergraduate training, which is pretty standard here in Australia to do frequentists first, both in psychology where we did statistics and also in the statistics departments. They don't talk about Bayesian until honours. Mm-hmm. So I first sort of started getting into Bayesian analysis when I started my PhD with Danielle Navari, and she would agree with this. Initially, I kind of hated it. I was so trained in this frequentist way that I couldn't think about it the right way.
Oh, that's funny.
But I think now I really appreciate the flexibility of the methods, and being able to use priors in a really specific way is really important for me. Mm-hmm. But I don't think I would never use a frequentist method. It's just I most commonly use Bayesian methods for the sort of work that I do.
That means, we're getting meta here, but that means you updated your prior about Bayesian methods and their usefulness. So that's great.
I did.
Well done on that. And actually, you work a lot with R and Stan, right? That's your favorite technical stack to do these kind of analysis, right?
Yeah.
And how did you came to using this actually?
So R, I think I started using in my undergrad. I was very lucky that I was one of the first years at my university to start using R as like a learning tool. So I don't really remember coming to it anymore. I do remember coming to RStudio and just thinking it was the most amazing thing ever. Stan I started when I started my postdoc at Columbia. And before that I was Jags.
Yeah. Okay, so like before getting into Andrew Gellman's orbit, like, okay, that's interesting. Okay, so let's dive a bit into what you're doing now, because you work a lot with survey data, as we said already, and these are usually very messy, as we can just see for polls, for instance. So can you tell us about those issues, especially missingness and non-representativeness, and, well, what this entails for inference?
I mean, it's everything, right? And it's funny that these topics come up most in survey data, because you see it all in people data, right? Wherever you have people, unless you're like a big government agency, people can refuse to do your survey or choose not to take part in your research, right? So wherever you're researching with people and they're providing you their data, you have an issue with non-representativeness, right? Different people have different opportunities to participate. And if you expect heterogeneity, or if you have heterogeneity, that impacts your outcomes. You have bias in your outcomes if you don't control for it or adjust for it. So I'm super passionate thinking about non-response. Missingness kind of, for me, falls into two camps. Like, there's the missingness that comes from non-response. You can recategorize non-response as missingness, right? And so that's kind of often how I'll think about it. But there's also the missingness that is not non-response through participants, but it comes through people self-censoring or not wanting to respond. So, for instance, we sort of talked about this, very recently put a preprint out talking about measuring sex and gender in surveys. And we were sort of talking about, well, as you move to more options when you measure gender, right, you've sort of got this move from having a male-female output like options, and then if people don't identify as either, they have only one choice, which is to not respond, which is missingness, right? Which you think of as missingness, but it's not missingness at random. It's a very specific type of missingness. And as you move to having more options, you can start to remove that, right? It's just kind of an interesting thing to think about. And I think like that's one of the cool things about doing statistics in this sort of area, because you get to talk to the people who are doing the research. The people who are doing the research know so much about non-representativeness and about missingness and about the reasons behind this and what's going on for people when they choose not to respond to the 10th page in the survey versus the first page, right? Like all these things play into it. I think like that's where you get this kind of like nice collaborations going, where you can kind of talk to people about things that they know are true in the data, but aren't normally matched when they start thinking about just the sort of bog standard tools that they would use when it comes to like statistics.
Yeah, I completely agree with you that you find these challenges in data like almost everywhere. I work a lot on polling data and survey data, so of course I'm gonna agree with you here. But this is almost always the case, and something I find sometimes frustrating is people using this kind of data as if they were, like kind of perfect random samples. This is always a big problem. I do a lot of electoral forecasting, and that's something I'm always, struggling with, is how to explain to people that you can't really take one poll completely seriously. You have to be very careful about how you interpret it. So that's like super crucial. But at the same time, I think people have this difficulty because this is a challenging task. I mean, I remember when I started learning about that, being like super confused about, I think the 4 types of missingness that you can have, like, so missing completely at random, missing at random, missing, and I don't remember the 2 other ones, and then you have like how you name those. So it's like MCAR, MAR, and so on. And you see that in papers and you're like, your head is exploding, like, wait, what is that again? But what I ended up finding very interesting and intuitive when thinking about those problems is to think that each time you do something to the data that's missing or not representative, you're assuming something. So if you just drop all of the missing data, you're actually making a strong assumption about what the missing data are. If you don't drop them but interpolate them with the mean, you're again making a strong assumption, etc., etc. And that's actually how I came also to Bayesian statistics, because then you have to explicit your hypothesis and your assumptions, and you can deal with this missing data. So this is like super interesting, and I'm guessing that's something you're emphasizing a lot in your work. Now I want to focus a bit more about how the methods you use to correct, or at least to be able to infer from missing data and from sample data in general. So if I understood correctly, you often use a method called multilevel regression and post-stratification,
yes,
which is abbreviated as MRP, or I think Andrew Gellman playfully refers to it as Mr. P. And so this is useful to deal with non-representativeness. So first, can you explain what MRP is to listeners?
There's this sort of idea that you have a sample and it's not representative on some variables, right? Some demographic variables.
Yeah.
And I think the first thing to realize is that no sample is really representative on all variables, right? You can always come up with a variable that it's not representative on. It's just the way of the world.
Yeah.
You have a sample that's not representative on some specific demographic variables, right?
For instance, like you have a sample and you think it's representative for education, but it's not representative for age or a race or stuff like that.
Right. And so you want to use that sample to predict something in the population, to get a population level estimate. And if you want to go down that route, you normally have sort of two options, right? The first option is to sort of do this weighted approach, right? Where you adjust the sample to the population by sort of calculating how many people would need to be, like how many people each person in the sample represents in the population. And they have a weight, and some people have more weights or less weights depending on how they've been sampled or included. And then you can do weighted estimates. Yeah.
And that's basically, if I understood correctly, that's basically what most pollsters, for instance, electoral pollsters do when they reweight their samples. They are doing exactly that. So that it means that, for instance, someone who is between 18 and 24 will be counted 2 times because the sample wasn't representative in the raw data.
Right. And it can get pretty complicated as you add in more demographics. The more demographics, the more variable, the more complex cross tables you have to think about.
And as you said, it's like you can't adjust for all the variables that exist. It's like you can't really, it's the same reasoning that you have when you say that you can't prove that something is not dangerous. Like it's not possible to account for all the sources of unrepresentativeness.
Exactly, right? So normally we focus on key demographics. And the reason, well, there's a bunch of reasons why we do that, but one of them is that we know them in the population, right? They're measured in the census or something that approximates the census, like the American Community Survey, which we can often use as a proxy. MRP is a little different, right? So rather than thinking about, I want to make my sample like my population on all the variables out there, or at least all the variables I know in the population. Instead, we think about, I have this thing in the population, and so we'll say like, because we were talking about cats, that thing is like whether you like cats. So I like cats. I think they're cool. I only have one, just so you all know I'm not kind of crazy. Alex might like cats or might not like cats, but he answers on a survey whether he does. And we know our demographics. And say we do that a bunch of times, right? And we want to do that. We want to use that data to predict in the population how many people like cats. Not a super important variable when it comes to censuses. They're probably not going to measure it on the US census anytime soon, whether you like cats or dogs. But we want to know.
Maybe we don't know.
So what we do with MRP, rather than trying to make our sample look like the population, we say, well, what's the relationship between liking cats and your demographic variables? So your demographic traits, right? And so we fit a model that predicts liking cats. This is sounding a little bit ridiculous now. Liking cats based on your gender and your age group and your education level and your race, ethnicity, all these things. And so now we have a relationship, right? We have a model that we can use to do prediction. And essentially with MRP, we have our population that we've summarized into a very nice post-stratification table, right? Which has all of the different combinations of demographics and the number in the population, right?
Yeah.
And then we predict for each cell the probability that this cell likes cats. And we're still making assumptions because we're saying within each cell, people are exchangeable, or you can sort of replace them in and out. But we make this prediction and then we reweight by the size of the cell. So it's a prediction-based method. And then we can get our estimate for the proportion of people in the population who like cats, of all things.
Yeah.
They're doing the same thing, right? Weights and MRP, but they're going about it in very different ways.
It's like super interesting. I love talking about this method all the time because it's like, it seems complicated, like in the name, it's like multi-level regression and post-stratification. But then when you get into the details, it's actually quite straightforward. It's like you have a sample, as you said, and you have each respondent. For each respondent, you have his or her demographics variable. And then you know that, for instance, in the Melbourne area, that many people are in that demographic cell, these many people are in that demographic cell, etc., etc. And then you do, as you say, the predictions based on only the sample data, and then you reweight based on the population cells that you were mentioning. So that's why also it's multi-level, because you have two levels. You have the sample and then you have the population level.
Well, actually, it's multi-level because you're using multi-level models. So you have random effects in this model, right, which regularize things down. And that's kind of important, right?
Yeah, that's also the nice thing. It's like also a very nice thing of this method. Like you have like partial pooling and shrinkage of parameters baked into the method.
Right, which is important when you start thinking about how difficult it is to weight by adjusting for a bunch of different crosstabs, right? The more crosstabs you have, the smaller the cells are getting, the noisier things are getting. One of the nice things about MRP is we can pool information together a little bit, right?
Yeah, and so that means you won't be, it relates to something we said earlier, that you don't want a model of the population whatever you're trying to infer. So here, the percent of people liking cat in the population, you don't want your model to be too prone to any one survey that enters the pool of observed data. So that's why having this pooling of information is important, because sometimes you have a poll that enters that seems to be an outlier. And so you want to be able to say, okay, this one is an outlier, but is actually pretty representative in its sample. So we should update our parameters quite strongly. But this one is an outlier and is really weird. Like it's missing a lot of demographics or stuff like that. So then your model won't be pulled towards the estimates of this poll too much. Like it will stay towards the population estimates, right?
Right. So now you're talking about poll aggregation, right? And sort of understanding that some polls or some surveys, some sampling methods have higher quality than others, right? And by quality, we're talking about response rate and also data quality and the frame. There's lots of things that go into trying to get it that people were really interested in, which is often the population.
Yeah, exactly. I put that all in the air, but it's quite natural that you're like, it's also where shrinkage of information and hierarchical modeling it's super valuable. But before maybe going into these, I think you answered why and when MRP is useful. So maybe do you have a nice example that you used in your work to do that, or maybe the cat example is enough, you think?
The cat example is the one I use for tutorials a lot. I actually have nice decks and decks of slide decks that have like little simulated populations talking about whether they like cats and whether they have hats and they like cats and like all sorts of different things that you might want to think about. Because while it sounds quite simple, it actually turns out to be fairly complicated, right? Like most things, you push it an assumption and things kind of start to slide a little bit.
Estimating population estimates is hard.
Oh man, so as soon as you don't have demographics measured, you want to adjust by something that's not measured in the census or measured a little differently, it's going to be a bit of trouble for you. It's not going to be easy.
Yeah, definitely. And so, of course, a podcast is not very visual, so I encourage people to take a look at the links I will put in the show notes. There will be a lot of links to a lot of your papers and also tutorials and vignettes you did about MRP. That's really how you will understand the method. I think here it will give you an intuition, but then you have to go and read and see the examples exactly as you said, like with the cat example or any other example to really understand how it works. And so there will be your examples. And I also put an example in Python and PyMC3 because there are all listeners who work with Python and PyMC. And so there is a very nice example written by Austin Ratchford, who is one of the PyMC core devs. And yeah, he's like going through an example like that to estimate, for instance, I think it's the support for gay marriage in the US at the state level based on national polls. So it's exactly a kind of very useful example. Now, something I want to focus on is actually how do you choose priors? Because as I think everybody who used multi-level models one time noticed, choosing priors for a hierarchical model is always challenging. So I'm guessing it is too for MRP. And you actually have a recent paper about that co-authored with several people that will be in the show notes. And it's about choosing structured priors to improve MRP. So what's your advice here for practitioners?
Right. So it's interesting. So the paper you're talking about, we were sort of talking about, so with MRP, we sort of talked about before, when you model these demographics, you use a random effect, right? Which assumes you sort of pull everything towards the model or towards a central mean if you just have a simple model. And what we were thinking about is that's kind of strange, right? For a lot of the demographic categories that we're using, it doesn't make sense to pull towards the global mean. It makes sense to pull towards their neighbors, right? So in the paper, we talk about age. An age group is a very common variable to include in your post-stratification matrix. Very, very common to include. And so maybe it makes sense to pull people towards like a random normal distribution, but we thought it would probably actually make a lot more sense to do a model that pulled age groups closer towards the age groups closer to them in time, right? Makes sense. So that if you're 18 to 25, you get pulled towards 25 to 35, right? Rather than towards the global mean or anything like that.
Yeah, super nice. Yeah, okay.
And that makes sense, right? And then we even pushed it a little bit further and we thought about, well, what about spatial models, right? If you're doing a geographic variable, does it make sense to have a geographic random effect, or does it make sense to have like a spatial component to your model, right? So these are things we've known about Bayesian statistics, like that we know these priors and this way of sharing information is good, but we're just sort of thinking and pulling them into that MRP context. And if you think of them all as this type of regularization of like shrinking a little bit towards sensible targets, then they're all doing a similar sort of thing. They're all regularizing just a little bit in the ways that you want them to do. I guess more broadly, talking about priors, I literally can't talk about priors without saying prior predictive checks a whole bunch of times. They're so useful. Have you had folks on your show talking about them already?
Yeah. I think it's something I like maybe emphasize a bit too much. But yeah, I'm definitely in your camp. Prior predictive checks are awesome, and especially for hierarchical models, because you have to define priors at for instance, at the population level, but you don't really know what that means on the outcome scale, and you can't know that before you do some prior predictive checks and prior predictive plots. So it's like super important. Yeah, completely agree.
Yeah, I can't emphasize them enough. Yeah. When I first started, I just used what other people use. Never do that. Always think about the context and don't feel bad about it. Like, I can guess priors pretty well these days using a logistic model because I fit a lot of logistic models. But as soon as I have a different link function that I'm using, I do prior predictive checks to understand it properly, right? It's super, super important.
Yeah, this is so valuable advice. And it's exactly the kind of advice I gave in my PyMC on talk that I did like a few weeks ago. And I actually fitted a multinomial softmax regression, because like I work a lot on French elections and we have a lot of parties. So unfortunately, you can't use the binomial. So you have to use multinomial. And in that case, it's even harder to think about your priors because you have all these all these categories and everything is interrelated. So it's like a giant interaction machine. And because of the softmax, you have ceiling and floor effects. And so, yeah, basically what I did there, now I have an intuition about what a good prior is or not. But what I did there at the beginning is just, okay, I have my population mean, which is a normal. And okay, let's just say it's a standard deviation of 10. If you do that with a softmax and a multinomial, you will get completely absurd results. It's like you're in a dictatorship, you have one party at 100% and then all the other at 0%, so, and you can't really see that before you do prior predictive plots, exactly as you say.
No, you might even think that they're more reasonable to sort of go a little wider until you do these prior predictive checks. I find too, it makes me much better at interpreting my parameter values. I don't do a lot of parameter interpretation these days, but just doing that quick look to make sure things look normal, normal being not crazy values. It's also useful to understand the realities of what some of these variables mean in terms of the outcome variable.
Hey folks, as I told you at the beginning, this episode is brought to you by Tidelift, and I'm really proud of it. In a nutshell, Tidelift helps organizations effectively manage the open source behind modern applications, including the tools to create customizable catalogs of non-good, proactively maintained open source packages backed by Tidelift and its open source maintainer partners. For instance, PyMC3, that I'm sure you all love, is part of the Tidelift subscription. So if you are using PyMC3 in your organization, you can seamlessly and efficiently integrate it into your organization's software policies and workflows. Sounds nice, right? So go ahead and check out tidelift.com to learn more. Going back to your paper, I'm curious. So first, how do you define structured priors? What does that mean? Because I was curious. That's the first time I heard about such a term.
To sort of encapture this idea that you have a structure in your demographic variable. You have an underlying structure. It's not just draws from an unordered categorical variable like eye color or something. It has a structure to it. So when you think about it, it's actually quite hard to think of demographics that don't have a structure to them, but something like age group definitely does, something like education level definitely does. Geographic variables tend to have structures, right? Once you get to state, it's a little bit fuzzier, but sub-state, zip code sort of level, you do have geographic sharing. And I think sort of just thinking about the structure of the variables and then thinking about how the priors encapsulate that knowledge.
I'm guessing you're explaining all that in the paper, and I didn't have time to read it yet, but definitely will, because it's super interesting and it will be in the show notes again. How do you relate all that, for instance, because what you were saying about, for instance, if you have someone in the 18 to 24 age group, you want him to be pulled towards the 25 to 40 age group and not to the 75 plus. How does that work concretely, mathematically? Do you use for instance, a GP, a Gaussian process would do? You have a covariance matrix that relate all of that, or how do you do that?
We used AR1 priors in the paper, but I think there's no restriction on this, right? And so you can see in other work, so Marta and Paul and Aki and I was the smallest author in this paper, so I don't feel bad talking about it, did this really interesting work where I think Paul and Marta fit splines over time, which was really neat, right? And this is drawing the same idea, right? You want to fit and model something that happens over time, right? So you could put a random effect for a year, but that doesn't really make a heap of sense when you think about a variable, which I think it was political trust, something like political trust, which you expect to move with some degree of continuity over years.
I tried that random effect, varying effects, if you, whatever you want to call it, on year. Doesn't work really well.
No.
I think it's much better to use a time structure, as you were saying. So either splines or, okay, you used AR1 in the paper, or if you are lucky, you could use Gaussian process, but then you have computational limits sometimes. But yeah, okay, I understand what you're saying. So you need this time structure to have this covariance between the age group, and thanks to this covariance matrix, they get pulled towards the appropriate age group.
Right. So I think it's interesting too, because you have knowledge, right? You have knowledge. It's not just prior knowledge going in, but it's knowledge about the structure of the variables and the structure of like things that you would expect to be related that you're using to build your model up, right?
Yeah.
And so I don't know, I find that super interesting, right? Like how much you draw on your own knowledge about the world and also your wonderful collaborators who know the data a lot better than you and their knowledge about the world, right? And their knowledge about these things that you're studying.
This is fascinating. But actually, I want to talk about last thing about MRP now. And I love to do that in the podcast because we talked about how useful and really wonderful this method can be in a lot of cases. But I'm curious about its limits and its pitfalls. I'm wondering, when would you not use MRP?
Okay, so they're two separate questions, right? So I'll answer the first one and then the second one. So the limits and the pitfalls, you're completely relying on your data to be good, right? That's the first one. We're relying on our data to be sort of what it says it is on the box. And we're also relying that once we've adjusted for these demographic variables, there's nothing left. We were talking about different types of missingness, right? So once you've adjusted for these variables, we're assuming that you can kind of exchange everyone that's left in and out, right? So that you can do your predictions.
I guess you're also relying on having quite detailed poll data. Like you need the poll's raw data. So you need like one row is one person with each of its demographic variable.
If you have binary data, you can do it in counts using a binomial model. So you actually can do it using just like the number who said yes and the number who said no in each cell, and it works out equivalent.
But you need the demographic variable used by the poll, and you need this detail.
Right. You do. And then you need a good census, right? Or a good population level data. And that's not easy to find sometimes.
Yeah.
And you need to have a mapping between the two, right? So if your survey uses different questions to the census, you're going to be in some trouble, right? Because it's measuring potentially something different.
Definitely.
So that's kind of like the pitfalls. And I think it's really, really good. And I'm glad you asked me to be really honest about what they are and about what it means when they fall, right? And what we can do to check, prevent, protect against, and understand those. And that's really something I'm excited to research. The other side of it is when I wouldn't use MRP at all, right? So I actually construct survey weights I have for the poverty tracker, for fragile families, for big high quality surveys that are weighted surveys, right? They don't do a lot of this sort of MRP based stuff.
Yeah.
And so there's lots of benefits to weights, right? They're very clear to use. A lot of statistical packages will just take them in, right? So it means that a lot of people are equipped to do analyses, weighted analyses, without necessarily having PhDs in statistics, right? Which is great. In addition to that, right, you can do things with weights. So you can use information that's private that maybe you can't release publicly. So if you need to adjust by a variable like zip codes are private information generally, right? You generally don't release it in a survey. So you can use that in your weights construction, and the only trace of it is in your weights. Whereas if you're trying to do it with MRP, you have to have access to the private sensitive data, which you can't normally always get, or you have to come up with some sort of approximation, something else that you do instead. But it's never as good. And the last time, sorry, lots of reasons not to do it. The last time is where you have a really strong survey design and high response. The best example of this is my buddy Alan Riddle at University of Indiana, who's doing a great survey, and he's working on some sort of project where he was sampling books, right? Yeah. Sampling books from the 1700s, which is, a funny thing to do, but he was doing it. He was sampling them, and then they would kind of read them, and they would categorize them in a bunch of different ways.
This is awesome.
And it turns out, he had a stratified sample, so he grouped the books in terms of length and different book characteristics, right? So you have book demographics. I'm using quotes for your listeners, book type demographics. And you could imagine doing MRP with that, right?
Yeah.
Model the book in terms of the book quality, in terms of its book demographics, and then make a model that predicts it. But you have almost no non-response, right? There's like a couple of books you can't find, but mostly the books are there. If you sample them, they're going to be there in your sample. So the only non-representativeness you've got is your stratified sample, where you deliberately oversampled certain types of books to get like decent sample sizes. In which case, it's very, very easy to calculate your weights. You're not calculating like non-response weights. And so those weights are easy to use, right? They're easy to calculate, so you understand them very well. And they do a pretty good job. And they're really quick to use, and you can share them with people and have them use them too, right? There's a lot of reasons why you might want to do this. Mm-hmm. It just so happens with the sort of data I work with, people say no to surveys an awful lot, an increasingly large amount of time. So we don't have that luxury.
Yeah, okay. This is really super interesting. And it also highlights like how each time you're using a model, you have to think about how it interacts and fits with the data you are trying to model and like the generative process of your data and the story basically behind it. So it's like really, really great answer. Thanks for this detailed analysis of MRP's weaknesses. It's great. Because as you say, it's like knowing which are the weaknesses and when the key assumptions of a method fall apart, that then you can, well, either change course or try to improve the methods you're trying to work on. And I'm guessing that's a big part of your research is like to go into these shady areas to help MRP shine even more.
Yes, very much. And I think too, like there's a lot of reasons to want to be honest in science. And sometimes as like researchers in universities, we sort of have to like, you know, you write a paper and you want to say like it's a really great method so that people like your paper, right? But it's really important to be honest and considerate and to be very clear about the benefits and the costs and the limitations of what you're doing, because that's how we're going to grow as a field, as a group of people, right?
Well, that's another completely other conversation, but yeah, that's also something I'm often thinking about. It's like the incentives that often are in research, or at least some fields, like to overstate your certainty in a given paper, and that's always something that's not really good at least in science. And when I get to something that's true instead of something that make people shine or else. So, but that's completely another topic. I talked about that a bit with Daniel Likens in episode 18, if listeners wanna listen. Okay, time is flying by, and I wanna talk at least a bit about imputation, because you work also quite a lot on this. Of course, I'm sure listeners know that it's useful to adjust for missing data, and so I'm wondering what are main methods there for imputation?
Well, I mean, there's a few, right? So it's funny, you can actually think of missing data and causal inference and survey sort of statistics. You can think of them as doing the same thing. Just like in surveys, you're sort of imputing a whole new person, right? And in causal inference, you're imputing a counterfactual. And then in imputation, you're normally filling in a hole in your data, right? You're missing a variable, you're missing an observation in one variable that you might have in other variables, and it's kind of like cheese, right? There's lots of different holes. And so I guess like and I thought about a little bit, because you told me beforehand you were going to ask me this, how you would kind of break all these things up. And I guess it's sort of like there's a simple single imputation, right? Where you've replaced your whole with a single number. Yeah. And we don't do this with MRP at all. We replace our person with a whole posterior, right? Yeah. And then there's a sort of multiple imputation view of these things, right? So this is things like Amelia. I'm using R packages because I think of the different methods in terms of R packages for some reason. So something like Amelia, which is where you fit a multivariate distribution, normal distribution, over all the variables you're trying to impute. And so you have this big covariance matrix, right? And you fit this, and then you use this to draw new values, right? And you can use this, you can draw multiple new values, right? And you get this idea of imputation uncertainty, which is good. You do have to assume multivariate normal for that one to work. And so, some people think that works well. Sometimes the data I've worked with, it doesn't work quite so well. Something like income is just crazy skewed, especially somewhere like New York, where the tail is just like endless. And there's not many transformations you can do to kind of pull that tail into a normal distribution. Yeah. But there's also things like mice, which is sort of iterative equations. So you can think of it as like predicting one variable by all the other variables or by a bunch of other variables. And you use that model, kind of like MRP, to predict a new value for that hole that you have. And then you do that for all the other variables. So you're kind of slowly filling up all your holes. And then you do it again, right, with the new data in there. You keep going and going and going until it converges. And then you have something like MI, which is another package that does similar sort of thing to mice, but with a Bayesian model underneath it. Not like fully not like MCMC Bayesian, but it's sort of got a Bayesian sort of underlying it. It's got priors and things, yeah.
Okay. Yeah, I see. It's always like missing data imputation is always like kind of always statistically heavy, and hard to explain. But this was clear to me, but also because I recently read there is a really good chapter about missing data in Andrew Gelman's Activatories and Jennifer Hill's last book, Regression and Other Stories.
Yeah.
Yeah, they talk about exactly the kind of method you just mentioned. So if people are interested, I would refer them to this book and also to episode 20, where the 3 authors went on the show. But yeah, that's definitely something interesting.
Yeah, it's kind of interesting to me that we think a lot about missing data imputation when we think about causal inference. We spend a lot of time thinking about our models and how we do it and what the issues with it. We spend a lot of time, or I do, with MRP, thinking about my models and what the issues with it all are, right? But then you think about imputation of like just a Swiss cheese sort of data set, a lot of little holes. And a lot of times you end up just plonking it into one of these algorithms that does it for you, and you get a bunch of different imputed values for it. You don't, think too much about whether the model's correct, what are some of the issues with it, was their model's misspecification, all this other stuff that could go on.
Definitely. And that's actually a great segue to what I want to talk about, which is, again, what do you think here? Because it seems like a very active area of research, missing data imputation. So I'm wondering, from your point of view, what are still the main weaknesses of the current methods, and, where you would be very skeptical of not to use that, or be very careful about how to use missing data imputation?
So I don't know the most recent literature properly. I don't think that I know it well enough to be able to say that. I will say that I've had issues with Amelia type methods, that multivariate normal type methods, when I've had skewed data. And, income is a very skewed variable, and I've worked with that a lot. And that can cause some big issues for you, because even if you do a transformation of it, if it's skewed enough, it's still skewed. That's just the reality of really, really skewed data.
Yeah.
I do prefer the sort of like iterative equation sort of approach better, but it's slower, right? It is slow. And so you have to balance out that sort of like efficiency of time versus efficiency of like actually just doing the computation.
That's one of the methods you mentioned earlier, the iterative approach.
Yeah.
Yeah. And thanks for your epistemological honesty of saying that maybe you don't know enough about that. I appreciate that. That's something I really, really love on the podcast.
The more I work in science, the less I feel like I know. Just generally, I feel like I'm not learning. I feel like I'm learning so much every year, and all the time I'm learning lots and generating new information. But yet, I feel like I know less about what I need to know.
Yeah.
Right. It's a funny experience.
Yeah, I know. I completely understand the feeling. I mean, as I said earlier, we had the first ever PyMC on, we said PyMC on, but it's PyMCCon as StanCon, And so it's I really loved this day, because it was really awesome to meet all these people and watching all these talks. But then it also leaves you with a feeling that you're like, surely there is so much I don't know. And it's I don't know anything, actually. So I understand what you're talking about. But that's also something good, something I wish more people were able to publicly acknowledge, So I'm definitely for this kind of epistemological, honesty. Let's talk now about causal inference, because I really want to talk about that before we close up the show. You mentioned that a bit already, but how do all these statistical methods help you do causal inference in the social sciences, which is something that you're very interested in? Basically, what I'm wondering is, do you have a whole workflow from survey data to causal inference?
So there's something interesting about that. So oftentimes surveys aren't interested in causal inference. I find that you see a lot of so the sort of causal inference I'm interested in is sort of experimental design. So it comes out of experimental manipulations, right? There are other types. I just don't do much work with them, right? The quasi-experimental, the natural experiments. I don't do a lot of work with those.
Yeah.
But they exist in that, good things to do, opportunity arises. So what I'm really interested in is this idea when you do experiments, right, you have people come into your lab or your office or whatever, and they do some sort of experiment on a computer, they poke some dots on a screen, something like that, and you learn something about how they react to different scenarios. And if there's not a lot of heterogeneity in the population, that's fine. However, if there is heterogeneity in the population, and we have very good reasons to think why there is, then suddenly you need to think very hard about the people who are coming into your lab to do studies, right? And so for me, there's this great connection. So surveys are really talking about generalization. For me, they're generalizing to a population, which is a really exciting thing, and it's a really difficult thing. And one of the things that I'm really interested in and think a lot about in terms of causal inference in this experimental world is how do we generalize that research to a general population when we know that the general population doesn't have the opportunity to take part? That's the reality. And what does that mean, right? And sometimes that's fine. There's no heterogeneity. The population's relatively homogeneous in terms of the effect we're studying, right? Which can be true. And sometimes it's not true. And how do we know the difference, and when does it matter? And I don't know the answers to all of this, right? But there's like a bunch of cool people who are sort of thinking about this. And I just think it's really, I don't know, it's exciting, right? To think about.
I think these are very challenging questions that if I understood correctly, you try to tackle in your own research. But these are like still a very active area of research, and we don't know a lot of answers. We don't know the answers to a lot of these questions. I'm guessing that's also why it's super interesting. And so actually, how do you go about working and like thinking about causal inference? Do you have some resources for listeners that you could recommend them?
There's a really good paper by Jennifer Hill from 2011. I'll get you the name of it, and you can put it in your show notes.
Yeah, definitely.
That is just a super nice way of thinking about it. And it is in this terms of this like predicted outcomes, which sits really well with my other research, which is also about predicted outcomes. And so this framework, it works really well for me to think about it this way. There's like the Judea-Pell sort of way of doing this with do algebra and things like this. Like, it's fine. It just doesn't sort of click well with my head. I don't find it very intuitive. So like this sort of Jennifer Hill's framing, especially in that paper, which I'll get for you, I think is really useful to think about. Because you're starting to think about differences between your treatment and control group, right? And then once you're there, for me, it's not a huge, big step, but it's the step that I'm really interested in, is thinking about the differences between your experimental group and your population, the folks that you'd like to generalize your experimental results to. So it's kind of two steps. And I don't know all the answers for that yet, but I'm super excited by it and would love to know at some point, right?
Yeah, me too. And so yeah, we'll definitely link to this paper by Jennifer in the show notes. And again, there are super interesting chapters about causal inference in regression and other stories that I'm guessing Jennifer wrote. And yeah, this is super enlightening. I'm actually planning to invite Jennifer on the podcast. This will be for 2021 because she was like super busy in 2020. But I really hope she'll be able to come on the show and do a whole causal inference show with her. That would be really amazing. And yeah, that you mentioned also Judea-Pearl's framework, which is based on do calculus and directed at cyclic graphs, which is very valuable too. It's used in other fields, maybe more in more computer-heavy fields. I know Richard McElrath, for instance, who works a lot on anthropological data, uses that, and he likes it. He emphasizes it a lot in his book, Statistical Rethinking, the second edition. There is a lot of very active research on that, and that's really great.
It's exciting.
Yeah. Honestly, that's really great to me to see this happening like this, thinking that, okay, when you have your statistical estimates, you're not done. You can't really call that a day if you want to do causal inference on that. You have to think a bit more, and there are more steps to it than just taking a survey data, getting model estimates with MRP, for instance, and then call it a day. Unfortunately, that's not that easy. Not to say that MRP is easy, but it's like it highlights how difficult it is to do real good causal inference.
I mean, this is true. I would say fortunately, though, because it's a wonderful thing to be able to continue to grow and learn. And like, this is a wonderful thing for us to be able to do, right? If all the knowledge was known, it would be boring.
I agree, but I'm guessing people not in research could disagree,
I understand this. Trust me, some days.
Yeah. Again, based on all we talked about here, I know you're not yet teaching Bayesian methods, but I'm guessing it will come one day because I know you love teaching. So if you had to teach Bayesian methods, what would be the essential skills that you try to instill in your students, our rules of thumb?
Yeah, I guess I wouldn't want them to learn rules of thumb. I would want them to learn workflows and procedures and ways of thinking. I think that's much more valuable because the rules of thumb, like you say, it's an active research area. It's changing and it's going to keep changing. And I'm sort of sorry for that as a scientist, but I'm also super glad for that as a scientist because it's so much fun. It's, mixed feelings about that. So what I'd really like them to learn is workflows so that they can generate their own knowledge and own understanding, right? So things like prior predictive checks. Rather than telling people the right prior to use, I'd rather they learn how to think through the ways we select priors and things like building up models, right? Which is super useful to sort of learn what each step of the model does and how they interplay together and understand your data and making sure you understand your, each step of what you're doing. I've been thinking a lot about Bayesian workflow for other reasons, right? So I think that's what I really want to emphasize, this idea of workflow and understanding, because I think it builds deeper knowledge and also longer knowledge with a longer longevity.
I completely see where we're coming from with that, and really agree because, as you say, also it's hard to have hard rules of thumbs when stuff are moving so quickly. You say so. Plus, it's like if you want to future-proof your statistical analysis, it's better to learn how to generate this knowledge and how to think, basically. It's better to learn how to think than having someone tell you how you should think and how you should do this or that. So definitely.
It makes you a better communicator too. And I think that's the other side of it is the people that I teach will go out and do data analysis and tell people about it, which is amazing. So cool. But ideally, I'd like them to be able to communicate what I communicate, right? Which is where things don't work and the uncertainties we have about it and the things we're not sure about and the interesting things that were kind of unexpected and, all of these things that play out and we all know play out, but they're really important to communicate to the people who are using that information to make decisions.
Yeah, definitely. Plus, and as we already said, I think earlier, communication is key and super important, especially when you're giving the results of your models to non-statistics people and even to statistics people. But yeah, you were talking about the Bayesian workflow, and I think you took part in a paper that just came out 2 days ago with a bunch of people. I know Aki was on there, Dan Simpson.
The monolith paper, was it 77 pages long by this point? It was a very long paper.
Yeah.
And I still think there's so much we don't know about it. So there's still so much room to grow.
Yeah. And this paper looks amazing. It's already in my reading list. I downloaded it this morning. So really hope to get to it soon. Thanks for doing this. Looks really amazing. I will try to heed your advice on all of these. I'm writing a book right now with Oriol Abriel about Bayesian statistics, so I promise I'll try to heed your advice.
There is levels of learning, right? So there's a certain level where rules of thumb are very protective. They protect you from doing silly things. And so that's really good.
Yeah.
It's just you sort of want to build into that a way of understanding them as well, I think.
Yeah, because you don't want rules of thumb to get in the way of just thinking. You don't want rule of thumb as an excuse for not thinking about your model and your data and so on. So yeah. Okay, we're getting short on time. I don't want to take too much time from you. So unless you want to do both questions, I think I'm going to ask you just one question more before asking you the last two quick questions, So okay. It's up to you. Either we talk about your teaching about the data ethics at Monash, or we talk about what the future of MRP causal inference look like to you. I actually want to ask you about your actual teaching, because you do teach at Monash University and you teach about data ethics. So how does this course go?
It's an interesting course, right? So the actual course is data analytics and visualization, right? Data visualization and analytics, one of the two. So the course isn't about ethics itself. But what we did was we kind of viewed it as one of the first times that people in our course would be sort of analyzing data for themselves, right? They would be downloading data from the web and they would be doing different analyses with it and different visualizations with it. And so we talk about a lot of the things you talk about when you start working with data, which is like how you manage data and how you get data and how you read data in and all these sort of things. But one thing that was really important to me was talking about the ethics of data use. And I think it's one thing that I think we really need to make an effort to talking about because it doesn't get talked about a lot, right?
Yeah.
And so this comes up for me all the time because all of my data comes from people and there's always ethical considerations and response considerations and all these things that play out in it. But I genuinely believe that almost all data has ethical considerations. And by that, I mean it has limits in terms of what we can say. It has people or things or like realities, world realities that it's representing. And we need to be very mindful of that as we talk about it. I was super lucky that I was allowed to kind of weave some of this through in the assignments, and we had a little course where we talked about data fairness, a week where we talked about data fairness, which was good. But I think it's one of those things that like more and more I think about how the work I do impacts people. It's kind of like you have to understand that it's a compromise, right? To understand that people have unique experiences, right? Which is true. We understand that people have unique experiences, but by doing survey statistics, we literally lump people together into different categories. So you have to understand that this is an approximation that we do to be able to do a statistical thing, but it's never the reality. And so there's this like duality of understanding the decisions we're making and also why we're making them. So that's my little spiel on ethics. I love data ethics. It's really interesting. I'm not an expert in it, but I think it's really important for all of us non-experts to think about it at least.
Definitely. And is it an undergrad level course or master grad?
Undergrad combined with masters. So I think it's like 2/3 masters, 1/3 undergrad.
Okay, nice.
Yeah.
Is there, like, I don't know, a GitHub repo somewhere people can access or something like that?
There's a web page that my co-teacher has. So I could direct you to that in the show notes. That sort of has the slides that might be interesting to folks. Yeah, that's probably the best resource I can recommend. And we're still working on it. So if people have comments, I'm super interested in like ways we can make it better.
Yeah, definitely. We should add that to the show notes.
Yes, please do, because otherwise I'll forget.
Before we go to the last two questions, I have a lot of questions about data ethics, but you've already been so generous with your time. Maybe you can come back on the show and we talk about that when you have, more samples from your data ethics course. But just before letting you go, I'm really curious to have your opinion on this question. What does the future of MRP and of causal inference for social science in general look like to you? I mean, which advances are particularly exciting to you?
I'm really excited to start thinking, and I've been thinking about this a bunch, but I don't have any publications I can point folks to, thinking about validation and testing some of these assumptions. So we've talked a lot about these assumptions that come out when you do these sort of methods. And no matter what sort of method you're doing, you always have these assumptions. You can't get around them, but you can test for them and you can kind of check. So if this assumption is true, then we'll see this, right? Mm-hmm. And so that's really an area of my research that I'm super looking forward to digging into a little bit more, just understanding what's going on with these methods a little bit better and also understanding how we can test a little bit better as well.
This is fascinating. I hope you'll get time to work on that. I can't wait to see the results of this research. Okay, Lauren, before letting you go, I'm going to ask you the two questions I ask every guest at the end of the show. So the first one is, if you had unlimited time and resources, which problem would you try to solve?
I thought about this a bunch. I would love to know how cognitive processes sort of play out as we do data analysis, right? It's sort of like the epitome of like my whole career, right? To understand these things. I would love to know it. But I was thinking with unlimited resources, you could probably do that with limited resources, and hopefully one day someone will. But with unlimited resources, I would build a really good census with lots of different questions, so we know a lot about the population. And then we can do really efficient post-stratification. And that's something you couldn't do without unlimited resources because it's very expensive.
And I'm guessing you want to do that on a global scale, right?
Oh, yeah, completely. Standardized questions, but also respecting that different cultures and countries have different experiences. So some way of doing that would be great.
Yeah. I love it. It's like, I think it's one of the most original answers I got to this question yet, but I really love it. It's like very, very nerdy answer. It's perfect. Thanks so much. And so second question is, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Okay, so this is lame because I actually couldn't think of a scientific mind that I would want to more than anyone else, right? There's certainly people I'd love to talk to, but I would love to talk to someone who, if you want to take the view that we're all scientists in life, right? I would love to talk to someone who feels like the statistics we're using in society don't represent their experiences, because I think those are the really interesting questions to answer, right? And those are the voices we don't normally get to hear, and sort of the further you go in life, the less likely you are to get in the same social circle, right? So that would be what I'd really, really love.
Very original answer again. You're definitely in the tails of the distributions for these two questions, but that's awesome.
What's the most common one?
For the first one, the most common one, I'd have to check all the episodes for that. Actually, I should do that one day. That would be funny to have the distribution of answers. I think the most common one is climate change. So we have like a lot of people who would like to work on that. For the scientific mind, though, it's really, really diverse. I mean, there are a lot of different people. I'm wondering, Aki came to the show and the show didn't air yet. By the magic of time travel, though, you should have heard Aki by the time your episode is out. I think I remember who he answered, and I'm not going to spoil it there, but I think it was the same as Andrew, so it's funny. But yeah, you'll see.
Very interesting.
You'll have to listen for that.
I'll have to listen. Yeah. Very cool.
Okay, thanks for taking the time, Lauren. It was really, really fascinating to dive into these statistical methods for the social sciences. I really love this literature, and I'm so happy you went on the show. These are topics that I hope a lot of listeners will love as much as I do. And no, I can't wait to try MRP on my own work now. I still have to find some data. That's the problem. Some good data, as we say. As we said, MRP is very sensitive to good data. As usual, I put resources and a link to your website in the show notes for those who want to dig deeper. So thank you again, Lauren, for taking the time and being on this show.
Thanks so much for having me. It's been really great fun.
This episode of the Learning Bayesian Statistics podcast was brought to you by Tidelift. Tidelift helps organizations effectively manage the open source behind modern applications, accelerate development, cut costs, and reduce risk with the Tidelift subscription, so you can create even more incredible software even faster. Learn more at tidelift.com. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.